Now you can see that we can write the Riemann double sum, or any Riemann double sum, in about 3 ways that make sense. And they're all equivalent. So the way we defined it is that we sum over all pairs I and j, one from taking values from 1 to n, fx star I, yj star, times this delta, so the change in area, delta A, ij, corresponding to the ijth chunk. Well, this is a sum actually over 2 indices, so I can write it as nested sums. So this is also equal to sum over j is equal to 1 to n. The sum over I equals 1 to n, f of xi star, yj star, delta xi, and out here I have delta yi. So this, inside of here I have yj star fixed, and I just sum over all these values, all the x values. I can also reorder that sum. It's a finite sum. I can reorder it. I've got I equals 1 to n, sum. So now I basically sum in the other index first. So now here, inside of the sum, I'm going to leave xi star fixed. And now I have my summing over all the y terms, and I have delta xi outside. And the picture is, well, I've got my rectangular domain. So this is the x direction, my y direction. This is from A to B, and this is from C to D. So I've got my rectangular domain, and I'm gridding it off. When I construct those tagged partitions. So I grid it off. I choose my x star, y stars. So this corresponds to a particular xi star, but the y's might change. So now in this direction, the x star might change. So on and so forth. We populate all these guys with a tag. And in one direction, so in the first guy, right, we're holding y fixed, that is, we're taking y slices, right, holding y fixed, and we're summing over all these entries first. So we sum over where y, this is say y1, this is y1 star. I sum over all the x values there. Then I would sum over all these chunks of volume corresponding to these little differential chunks of area. I sum here, and so forth. Right, so this is the picture for sum over j first. If I sum over I first, that corresponds to keeping the x's fixed, and I sum in this direction. So this picture corresponds to sum over I first. Well, if the Riemann double sum admits three forms, then we would imagine, and we would hope, that actually this also works for the Riemann integral, right? That is, I can represent the Riemann integral as just a nested sum of integrals where I'm leaving particular variables constant as I integrate. And these will be called nested integrals. And we have a theorem if f from R2 into R is continuous on the rectangle R is equal to AB cross CD, then the Riemann integral on R exists, and we have that the integral over R f x y differential with respect to the area is equal to the integral. First, we keep y fixed, integrate from a to b, f x y dx. So this is integrating over all constant y values, and then we put a dy out here, and this will be called a nested integral because this integral is nested inside the other. And it's also equal to, well, we can change the order. The integral from a to b, now the integral from c to d, f x y dy now, so we leave x fixed and we have a dx out here. This is great. This means that we actually have a procedure by which we can actually calculate this number that we defined earlier. So let's do a quick example to just see the mechanics of this problem. So let's integrate over 0, 1 cross 0, 1. This function x, y, dA. So let's do it in both nestings. So first, let's integrate over x slices. So integral from 0 to 1, 0 to 1. So we'll leave y fixed. So this is x, y, dx. And I have a dy out here. Well, inside of this guy, y is fixed. So this is equal to the integral from 0 to 1, y times the integral from 0 to 1, x dx. That's a dx, sorry. Dy out here. And so now we integrate this thing with respect to x. And what do we get? Well, we'll get 1/2 x squared evaluated to the limits. The lower limit is 0, so it dies. The upper limit is 1, so I ultimately acquire just 1/2 dy, which is just constant, so I now have 1/2 integral y dy, 0 to 1. And similarly, this is equal to 1/2, and 1/2 times 1/2 is 1/4. So now what would happen if we went the other direction? Well, this is also equal to the integral from 0 to 1 the integral from 0 to 1 xy, only now I integrate over y first and leave x fixed inside that nesting. Well, because of symmetry, of course, this is going to be a similar game. But now since x is fixed, I draw out the x variable. I have to integrate this guy. And you see that this will also equal 1/2 integral from 0 to 1 x dx. And you'll still acquire 1/4.